All right, let's go ahead and get started. Thank you all for being here. I am thrilled to welcome you all to Slack. My name is John Sorrow, and I've been lab director here now going on my 4th day. So thank you all very much. I would say on the one hand, couldn't imagine a better highlight of my first week than doing the Bay Area Research Slam with our colleagues from Berkeley Lab, Livermore, and Sandia. And also, I'm proud of myself for actually finding the room. So that's my first accomplishment. Before we actually get the show going, I want to say thank you. Certainly thank you to my colleagues from the other labs for joining me in the judges panel. Thank you to all of our speakers who will be certainly much more articulate than me. And so the sooner we can get to them, the better. But before we do that, thank you for all the folks who made the event happen. This will go off swimmingly. It'll be totally invisible, but that belays all the really, really hard work that a bunch of people did to make that happen. So sincere thank you to all of you for doing that. I am really excited for the rest of the afternoon, and I will turn it over to our science comedian, Brian Mallow, to get the show on the road. So Brian, over to you.
Thank you, John. Thank you, John. And see, no one thought you'd be able to hold this job this long, and look at you. 4 days already. Congratulations. So we have a really interesting and unusual event for you. I want to say hello to our virtual crowd or future virtual crowd that'll watch it online, and welcome this wonderful live audience. And I've met our contestants and they're fantastic. And if you don't know, what is a research slam? It's a lot like a poetry slam, but our poets are scientists, and they will each have a mere 3 minutes to present their science in a way that's understandable and appreciated by a general audience. So it's quite a challenge. They've spent years working towards this place, and they have 3 minutes to talk to you. Also, they've gone through quite a process, because each of the 4 national labs in the Bay Area has had a process of selecting finalists. So we will be seeing 3 finalists from each of the 4 labs. The 4 labs represented today are Lawrence Berkeley National Lab in the house, the Stanford Linear Accelerator Lab right here, our hosts for this amazing event, Lawrence Livermore National Lab, and Sandia National Lab. Today's event is live here. It's also on the Slack, Stanford Linear Accelerator Slack YouTube channel. You can see it there later, or you're watching it there right now. We have met we've heard our labs. Let's meet our judges, because that's an unusual part of this science communication event. They're going to be judged, and our judges are directors of our national labs. So we have from Lawrence Berkeley National Lab, Mike Witherell. From Slack, already 4 days into his term, John Sorrow. From Lawrence Livermore National Lab, Kim Badil. And from Sandia, Andy McElroy. So I'll tell you a little bit about what to expect today. I'm going to talk to you for a couple more minutes, and then we'll get started. We will hear from each of the 12 finalists. And in between each one, we're also going to be doing trivia questions. I'll be presenting you trivia questions, and we actually have some little prizes. So we're going to ask you, I'll take for each one, raise your hand if you think you know the answer. Some are multiple choice, some are not. They're a little more challenging. And then we'll give you a couple tries and see if someone can win each one. And we have prizes for each trivia question. Yes, there they are over to the side. You didn't get a chance to peruse them before the show, but there they are. All right. And we also, so when it comes down to the contest, we actually have 3 different awards. There's the actual award for the 2 finalists, second place and first place of our 12. But there's also going to be a People's Choice Award. So you will have an opportunity, whether you're here or watching online. If you're watching online, there will be a link in the chat. And if you're here, we'll have a QR code that'll launch the link, and you'll get a chance to to make a people's choice of our contestants. But then finally, if you see over here, we have this giant trophy. Let me bring it over here. What this is like I said, 12 finalists, 3 from each lab. When the judging is done, the lab that has the most points will be awarded this. And this is our 3rd annual Bay Area Research Slam. And we have in 2021, Lawrence Berkeley won. In 2022, Lawrence Livermore. And now we just have a blank slot there for the next winner. You know what? I was not given the criteria for the judging. Do our judges know the criteria? That would be useful. Maybe they could tell me. Here we go. The rules of the competition. The presentations are scored according to 6 criteria: significance of the research, contribution clearly specified, clear logical sequence, delivery and stage presence, presentation of background, ability to capture and maintain audience attention. They have 3 minutes and a maximum of 1 slide. I think everyone is using 1 slide, if I'm not mistaken. And there you go. So those are the rules. The only thing I wanted to add is, of course, we're very environmentally conscious. I wanted to assure you that today we are only in the entire production, the lights, the microphone, the cameras, we're only using recycled electrons today. No electrons will be created or destroyed in the course of this program. I can assure you that's a fact. I'm not even a scientist. Unlike so many of the people here, I'm not a scientist, I'm not a doctor, although I do play one in the broken dreams of my parents. Thanks for laughing. That wasn't a joke. I was opening up to you. So, you know what? Let's get things started. I'll be here. You'll see plenty of me. So let us begin by bringing on our first finalist. She comes to us from Lawrence Livermore National Lab. The name of her talk is Climate Change is Hot, Electrochemistry is Cool. Please welcome I said she, I'm sorry. This is just a practice, right? We're going to do a second. Let me do a second take of that because I misgendered our first contestant. So he comes to us from Lawrence Livermore National Lab. Climate change is hot. Electrochemistry is cool. Addie Pajarati.
Let's talk about an innovative solution that tackles one of the hottest issues of our time, climate change. We all know that global warming is a pressing concern of the 21st century. The rise in carbon dioxide from human and industrial practices are its leading causes. With the ever-growing population and increasing energy demands, this situation is only going to get worse unless we do something about it. That's where electrochemistry comes in. Electrochemistry uses electricity to drive chemical reactions. It is an attractive approach because we now have access to cheap, stable, and sustainable electricity as a source of energy. Additionally, it gives us better control over chemical reactions, has a potential for industrial scale implementation, and it works near room temperature. That's why electrochemistry is cool. A typical electrochemical device consists of 2 major components, anode and a cathode. My research journey began by developing a cathode that would reduce carbon dioxide, the most prevalent greenhouse gas, into ethylene, a vital polymer precursor for a billion-dollar industry. And I was successful in doing so. However, I realized that there's a significant energy loss at the anode. You see, anode produced oxygen, which not only consumed a lot of energy, but was also a low-value product. So it was clear I needed to find a better solution. That's when I asked myself, what if I could tweak this anode system to create valuable chemicals sustainably? And that's exactly what I did. We now have a device that not only converts CO2 to ethylene on cathode, but on the anode, it converts biomass, a renewable feedstock, into chemical building blocks for plastics. So imagine converting something that is naturally occurring, like honey, into something that we use regularly, like water bottles. This innovative approach produced 40% more valuable chemicals and cut down the energy consumption by an impressive 6%. Building upon this success, my next step is to scale up this technology. By doing so, I aim to provide viable means to decarbonize industrial practices. In conclusion, climate change may be hard, but with electrochemistry, we've found a cool solution. Thank you.
Thank you, Addie. All right, and now we're going to begin the part and throughout the program where we need a little audience participation. It's our first trivia question. So, which lab pioneered the development of the clean room? Is it Lawrence Livermore, SLAC, Lawrence Berkeley, or Sandia? Raise your hand and I'll take a, come on, yes. Sandia it is, we have a winner. And you're being brought a prize right now. Do you work at Sandia? Did we have any rules about this sort of thing? Okay, well, how did I know that? Do I get a prize for guessing that? What lab you worked at? I will assume anyone that answers any question correctly is associated with that lab or the actual research. Our second finalist. Do I need to allow you a little time to compute your judgment of our contestants? Okay, no, because you're professionals. Our second finalist, coming from Sandia Lab, her talk is called Taking Off, Fueled by Biology, Using Yeast to Make Sustainable Aviation Fuels. Please welcome Valentina Garcia.
Let's fly away.
Like many of you, I really try to reduce my carbon footprint. But every year, I hop on a plane in foggy San Francisco, California, endure a long, bumpy flight over the equator, and land just as the sun starts shining on the Andes Mountains in Santiago, Chile. Today, this flight is fueled by crude oil, a limited source of carbon that has been underground for a very long time. Unfortunately, this means this flight alone accounts for a quarter of my annual carbon emissions. But I'll never give it up because my cousins are always there when I arrive to give me a big hug and a ride from the airport to a warm breakfast. The reality is the aviation industry is absolutely essential for maintaining the interconnected world we live in, and there are no available technologies to make it sustainable. While I can arrive here today in an electric-powered car, batteries are simply too heavy to allow commercial planes to take flight. Plus, let's keep in mind that engineers, chemists, and physicists have spent well over a century perfecting the fuel-based way we trust to cross oceans by flying. So instead of overturning the whole system or never flying again, what if we could make a fuel that was sustainable? Well, I think it's finally time for biology to enter the mix. Biology may seem like a weird solution for making a metal machine take flight, but I work with this yeast, Rhodosporidium toluroides, Rhodo for short, that does two things incredibly well. It can produce a number of different compounds, and it is fueled by plant waste. Rhodo, in fact, naturally makes compounds that look a lot like those used to make jet fuel, and we have altered it to make exact matches. To produce these matches sustainably, we simply have to grow it on that sustainable source of carbon it loves, plant waste. Think of the inedible pumpkins sitting on porches across the country, or the leaves starting to fall from the trees in the Northeast, or even the grass we're frantically cutting back to reduce fire risk here in California. Rhodo could turn all of that into jet fuel. In my day-to-day work, I grow Rhodo on plant waste, and it produces these exact matches. So why aren't we flying on Rhodo's fumes today? Well, I only do this on a very small scale, and I maybe produce a teaspoon's worth of fuel a year. We need a lot closer to 45,000 Olympic-sized swimming pools in order to make the aviation industry sustainable. So in my current work, I am focusing on making more of each exact match by trying new, hopefully more efficient ways Rhodo can make them and testing my Rhodo in larger and larger batches. There is a lot of work to be done, but hopefully one day on a future trip to have breakfast with my cousins, you'll come fly with me and we'll fly away sustainably, fueled by biology.
Thank you, Valentina. And our second trivia question. Where was the National Energy Research Scientific Computing Center, NERSC? Did I miss something? Do you want to share with the whole class? Where was the National Energy Research Scientific Computing Center, NERSC, first established? I'm going to need some hands raised. I'm going to need, all right, well, incorrect. I know. That's where it is currently located. It's sort of a trick question. So do we give another person a chance? We've already narrowed down one wrong. Yes. Lawrence Livermore is correct. No. Yeah, it is. Okay. Yeah, sorry, I'm having trouble with acronyms. We got LLNL, LVNL, and it's all right. It was launched in 1974 as a computing resource for fusion energy research at Lawrence Livermore. In 1996, it was moved to its current location at Lawrence Berkeley. So nice try. That was perfect, actually. You were misled by the question. You fell for it. That was a successful trivia question. Kudos to whoever came up with the questions. Okay, so now we move to our third finalist. Coming to us from right here at Slack. The name of his talk is Learning Real Physics from a Virtual Universe. Please welcome Sandy Wan. Ewan.
When I was little, I would look up the night sky and ask, what is out there? Well, there are two things out there, mostly. Dark matter and dark energy. These are two mysterious entities that make up 95% of the universe. Yet, we don't even know what they are. You see, the problem is, we can't see them because they don't emit light and they don't absorb light. However, they do affect the positions and properties of all the galaxies in the universe. Thus, as cosmologists, we use galaxies as cosmic beacons to shine a light on the nature of dark matter and dark energy. That's why we built Desi and Reuben, two giant telescopes scanning the night sky and chasing down the positions and properties of billions of galaxies. And because of the finite speed of light from the furthest corner of the universe also took the longest to get here. Thus, by looking really wide and also really, really deep into the universe, we are mapping the universe, not just in space, but also in time. However, to truly understand the amazing data that these telescopes will bring us, we need enormous simulations of the universe. That's why I use the world's largest supercomputers to build the world's largest simulation of the universe. In fact, my simulations are several times larger than the visible universe, yet it still has enough detail to see the fine structure of individual galaxies. I actually do use my simulations to build the world's most sophisticated model of the galaxy, with so much fidelity that you can directly compare them to Hubble Space Telescope images of very distant galaxies. Just look at the amount of similarity between this Hubble image of one of the very first galaxy and the simulated galaxy taken from our simulation. So how do we actually learn about dark matter and dark energy from these simulations? Well, I actually created millions of virtual universes with our simulations, with different galaxy physics, with different models of dark matter and dark energy. And I trained an AI to help me pick out which one of these millions of universes look like the real one we see with our telescopes. By doing that, I can pinpoint with percent-level accuracy the exact properties of dark matter, dark energy, and galaxies all at the same time. Ultimately, by fusing the tremendous data that our telescopes will bring us and the true power of the modern computer, I can finally crack open the most fundamental mysteries of our cosmos. Thank you.
Thank you, Sandy. Unfortunately, there won't be a prize for best jacket. But our third trivia question. Are you ready, audience? What is the name of that galaxy? Our third trivia question. Here he comes. What was the yield of the fusion ignition experiment that took place at the National Ignition Facility on December 5th, 2022? This is not a multiple choice. Does anyone want to? Let's take a first stab at it. December 5th, come on. What was the yield of the fusion ignition experiment at the National Ignition Facility? Yes. 1.3 what? Units. 1.3 centimeters, 1.3 kilograms. What? I know I need a unit, but 1.3 is inaccurate. Oh, surprisingly, that's exactly the right answer from someone who clearly works for the National Ignition Facility. Knowing the yield specifically on December 5th, 2022. So give her, yeah, where do you work? All right, Lawrence Berkeley National Lab. That's right. I have to repeat for the benefit of our streaming audience. I'll sometimes repeat something an audience member says. So our next contestant, number 4, we're already almost 1/3 of the way through the competition, comes to us from Lawrence Berkeley National Lab. His talk is called Zero Energy Windows. Please welcome Ewan Gao.
We love large windows, but probably not on a hot summer day when the sun is scorching a room through the big window, especially when your air conditioning is down. Even if everything is working fine, it still consumes a lot of energy to cool down your room. Actually, your beautiful window could be responsible for staggering 30% of energy loss. The good news is our team at Berkeley Lab is developing technologies that can reduce this energy loss to 0 and even transform your window into a power generator. Well, when talking about power generators in buildings, you might first think of the roof-installed solar panels. They are made of opaque solar cells that convert sunlight into electricity. One method to add transparency to the solar cells is placing micro holes. These micro holes are small enough to be visible to the human eye, but large enough to avoid diffraction and interference. Solar window with micro holes looks just like regular window, but it can amazingly transform sunlight into electricity. But we didn't stop there. My study takes a step further by integrating micro shutters into the solar windows. These tiny micro shutters can open and close just like regular sized window shutters, but by electrostatic force from a voltage difference. Also, the micro shutters are designed to perfectly cover the micro holes on the solar cell. In this way, the unwanted sunlight is partially blocked by the micro shutters and partially converted into electricity by the solar cell. Also, the transparency of the window can be controlled pixel by pixel using the power generated by itself. When we combine this technology with smart home ecosystem, we can control the window by simply saying, "Hey Siri, dim the window," or "Hey Google, open the shutters at sunrise," or even "Alexa, display Merry Christmas on my big window." But let's take a moment to think bigger. Buildings are not the only place to apply this window technology. We can also use it in your cars. Imagine your car is parked in the hot summer sun, but the temperature inside your car automatically stays cool without consuming extra energy. Once this technology becomes mature, you can say goodbye to the ugly sunshade in your car and say hi to the beautiful, smart, zero energy window.
Thank you, Ewan. His whole family is here, apparently. Trivia question number 4. Are you ready? All right. Biochemist Jennifer Doudna, a Berkeley Lab faculty scientist, co-won the 2020 Nobel Prize in Chemistry. What did she discover? Obviously, you all know what all these acronyms stand for. What did she discover? CAR-T, Cas-Clover, CRISPR, or TALENs? I'm almost afraid. CRISPR it is. We have a winner. Can I, what lab are you from? Lawrence Berkeley National Lab. I know. Okay, we got it. All right, ready for our 5th finalist? Coming to us from Lawrence Livermore National Lab, the talk is called Igniting Tomorrow's Clean Energy, 3D Printing for Fusion Power Plants. Please welcome Wedi Mostopo.
Here comes the sun. Here comes the sun. I say it's all right.
As our society seeks for more sustainable sources of energy, something big happened here in the Bay Area last year. Fusion ignition. It's a process similar to the one powering the sun. It occurs when 2 different types of hydrogen atoms undergo a nuclear reaction and produce more energy than they consume. Now, the hydrogen fuel for a fusion experiment is usually stored in a spherical capsule. Now imagine a Cheerio cereal. If you focus on the hole in the middle of it, the capsule is around the size of that hole. Now it's pretty small, but currently it takes months to fabricate, assemble, and analyze these capsules because they need to be nearly perfect. On the other hand, if we want to have a commercial and clean fusion power plant using existing technologies, we would need hundreds of thousands of these capsules a day just to generate enough power. In other words, we need a capsule making process that goes 1,000,000 times faster than what we have right now without sacrificing quality. In my research, I strive to bridge this technological gap by using state-of-the-art 3D printing systems that can make capsules with a precision of around 1,000th the width of a human hair. And so far, they've given us at least 3 advantages. First, as opposed to taking weeks and months, I've shown that we can now make a capsule within hours and days, which is 10 to 100 times faster than current methods. Second, instead of having to assemble multiple different components, we can now combine them and 3D print them as one part, therefore simplifying the manufacturing process. And third, we can now make complex geometries that would be nearly impossible to make using traditional methods. For example, I've shown in my research that we can now produce foams that are simultaneously tough and lightweight by making them out of very tiny 3D printed fibers. I'm currently integrating similar foams into our capsules to enable a new fuel injection process. This process takes advantage of the unique interaction between the fuel and the foam, and is expected to increase the amount of energy we get from the fuel and reduce the capsule preparation time. And we're not limited to just capsules and foams. We can make other complex geometries and start exploring new physical phenomena. For now, my 3D printing research is focused on how we can make the best capsule possible in as little time as possible. Once we can integrate other advances in 3D printing systems that can make 100 to 1,000 of these capsules at once, we will have a system that can supply enough fuel capsules to a fusion power plant, our small-scale sun. At that point, we won't have to wait for the actual sun to rise and power our solar cells, because we'll already have a similarly clean power here on Earth. Thank you.
Thank you, Wedi. Our next trivia question. These trivia questions are like, if you like sushi, it's like the little bit of ginger to cleanse the palate in between our contestants. So, which DOE lab designed the world's largest high-performance optical lens ever fabricated? Slack. Wrong. That's so wrong, you have to be excused from the venue. Incorrect, sorry. come on. We've taken one. Now it's only 3 possible choices. Yes. Correct. Lawrence Livermore National Lab designed the optics for the Large Synoptic Telescope, the LSST, which were fabricated by Ball Aerospace and Arizona Optical Systems and delivered to SLAC in 2019. Ready to go. You get a prize and you don't. Sorry. That makes the prize that much more special because of the way I mistreat you. All right, our 6th finalist. Ready? Coming to us from Sandia Lab, the name of her talk is Microbes at Work, the Magic Behind the Palm Kernel Oil Production. Please welcome Karuna Wedi.
This is a story of a magical oil extracted from a fruit that grew in the rainforest and made it all the way into our home. It's present in the soap, it's present in the perfumes, and also in the medicine I take. It's a core ingredient in over 50% of the processed goods. Can you guess it? I know you guessed palm kernel oil, and you are right. Today, the world consumes nearly 60 million metric tons of palm kernel oil each year, and the demand is expected to be double by 2050. That means we have to double our land to plant these palm trees. In the places where the fruit is grown, the people are burning down millions of acres of rainforest, leading to the climatic change. But what if there's an alternative technology to produce this palm kernel oil to prevent deforestation? This is my work. To find a solution, I work on a microbe that naturally accumulate oils in its cells. These oils act as a building blocks to produce palm kernel oil. So I use these tiny microbes to produce the palm kernel oil with microbial fermentation, just like we produce beer from barley with the help of microbes. This sounds like a simple process, right? But the challenge is our microbe has all the tools which are necessary for the production, except for few missing screws. In my work, I provide these screws by designing a DNA with the detailed instructions and incorporating it into the microbe. And so far, I have introduced a slightly different DNA in over 100 microbial strains. And I'm amazingly successful, as 90% of the strains were producing palm kernel oil. Once the process is refined, our industrial collaborators take over the production on a commercial scale. Recently, they have released a commercial product, which is an alternative for palm oil. Interested? Google palmless. This technology with our microbes takes 6 days to produce the palm kernel oil. But if you were to plant the palm tree today, it takes 7 years. Who knew at the end of this story, a tiny microbe would be a magical solution in saving the rainforest? Thank you.
Thank you, Karuna. And she was our 6th finalist. That means we are halfway through our competition. And here comes our 6th trivia question. How many, it's such an obvious question too. How many corgi puppies can fit in the LSST camera? And we're giving you a seriously good hint here in saying that the camera volume is approximately 180 cubic feet. So remember, corgi puppies, we're not talking Great Danes, we're not talking Chihuahuas. This is corgi puppies. How many can fit in the LSST camera? And the units are corgi puppies. Yes. What, by an amazing, were you guessing? 240 corgi puppies can fit in the LSST camera. Ladies and gentlemen, the designer of the LST and owner and breeder of corgi puppies, apparently. Where are you from? Sandia? 240. I mean, does someone want to take a stab at a trivia question that they don't already know the answer to? Come on, play along with us. Our 7th finalist. The name of his talk is Measuring the Delay in Photoionization, coming from right here at the Stanford Linear Accelerator. Please welcome Taran Driver.
1, 2, 3 o'clock, 4 o'clock, rock. 5, 6, 7 o'clock, 8 o'clock, rock. 9, 10, 11 o'clock, 12 o'clock, rock.
Okay, so this week, the Nobel Prize in Physics was awarded for measurements of ultrafast electron motion. How's that for significance? The work that I'm going to tell you about is what me and my team did to study what happens when a molecule absorbs an X-ray. So here in red and blue, I've drawn a small molecule. And when it absorbs an X-ray, it gains energy, which it can then release by kicking out an electron. And this fundamental process is known as photoionization, and it's hugely important for modern technology. It helps us look at broken bones in the hospital and build the tiny silicon chips that we all have in our phones. Now, the tricky part about measuring photoionization is how fast it happens. On the atomic scale, you could think about it like a molecular firework. First, on the left, the X-ray arrives and lights the fuse. Then there's a small delay, and then the firework goes off and spits out the electron. And now, during this delay, the electron is burrowing out of the molecule. So measuring how long this takes can tell us vital information about the molecule's structure. But the problem is this can happen in less than 1 femtosecond. And this is quick. If I could take a step every femtosecond, then in a single second, I could run to the sun and back about 3,300 times. So although this delay was predicted by scientists 70 years ago, it's only now that we can measure it for the first time, thanks to SLAC's X-ray laser and a stopwatch we make from light. So here's how. Light consists of an electric field, which points in a given direction and oscillates in space. And we can immerse a molecule in light which is circularly polarized, which means that instead of oscillating up and down, the electric field spins around, completing, in our case, about 200,000 billion rotations per second. And the part to remember is that if an electron finds itself in an electric field, the field will kick the electron along the direction the field is pointing. So using SLAC's X-ray laser, we can shine an X-ray pulse on a molecule immersed in circularly polarized light. We know which direction the field is pointing when the X-ray lights the fuse. The field keeps spinning, and then when the electron is released, it gets kicked in the new direction the field is now pointing. And so measuring the direction the electron was kicked tells us how far our stopwatch hand has traveled, which is how, for the first time, we can now measure this tiny delay using SLAC's X-ray laser. Thank you.
Thank you, Taran. And we are on trivia question number 7. At which Hawaiian island does Sandia have a launch facility? Multiple choice: Maui, Kauai, Oahu, Hawaii. Yes, the Hawaiian in the back, no doubt. Hawaii. Incorrect. You are not from Hawaii, it turns out. In the back? Oahu. Incorrect. Is anyone really looking? Yes. Incorrect. Are we actually going to give this? Can anyone possibly guess the correct answer to this question? We're going to give you a second chance. As a matter of fact, oh, wait, am I right? Yeah. No, not Hawaii. We already said, you guessed one that was, she said Kauai. All right, you're far away. I didn't hear it. Kauai B was the correct answer. There it is. Were you just reading it off the screen? All right, so the Kauai test facility is a rocket launch range in Hawaii, operated by Sandia National Laboratories for the Department of Energy. The facilities and personnel support a variety of missions, including research and development, operational training, and test and evaluation. Coming to the stage next, our 8th finalist comes from Lawrence Berkeley National Lab. The name of his talk is Choosing the Floor for Dancing Electrons. Please welcome Bernard Field.
Have you noticed how your phone gets hot? You'll be scrolling along, watching TikTok dances or something, when your phone just burns through all its battery. This is a problem, and it's not unique to your phone. Data centers, the warehouses of computers which run the internet and AI, use more electricity than my entire home country of Australia. Our browsing uses more power than most countries. The reason for this ravenous energy usage is silicon. Computers contain billions of silicon transistors. Transistors work by shoving electrons, the carriers of electricity, through them, then blocking them with brute force. But electrons stumble blindly through silicon, wasting energy when moving and stopping. This is one reason we are approaching an energy crisis. So how can we avert this crisis? We need electrons to dance elegantly through materials, flowing and stopping with graceful ease. But electrons don't like moving in silicon, so we need a new material. That's where I come in. I researched the way electrons dance in exotic new materials, just a few atoms thick. Recent experiments found electrons dancing strangely in one such material. So I used computer simulations to figure out what was making these electrons boogie. Turned out it was because the electrons repelled each other strongly when they got too close, leading to a kind of electronic ballet. Although tiny tutus might be stretching the metaphor a bit. My simulations also found ways to control this ballet by changing the material it was grown on. This understanding helps us to choose the right dance floor for our electrons. From this, we found a material where, given just a little nudge, the dance changes from one which flows to one which is frozen in place. This metal insulator transition could be used to make more efficient transistors for computers. My research has found new materials in which electrons can dance. If we can teach the electrons in computers to dance, then we'll save a ton of electricity, make your phone last longer, and avert the computing energy crisis. And that will be something worth dancing about.
Thank you, Bernard. Also getting a special prize for most elegant bow. We have a trivia question, right? Trivia question 8. Seems like it's from Superman's home planet of Krypton or something. What does a klystron generate? Is it ultraviolet rays, X-rays, or microwaves? All the way in the back. C, microwaves. Although, as a pun, it doesn't work. You can't see microwaves, but that is the correct answer. Give him a prize. And let's meet our 9th finalist, coming from Lawrence Livermore National Lab. The name of his talk is 3D Printing the Future, Designing Additively Manufactured Materials for Extreme Environments. Please welcome Brandon Zimmerman.
New materials expand the boundaries of engineering. There's a reason we label periods of antiquity, the Bronze Age, the Iron Age, the Silicon Age, by the materials that define them. Advances in 3D printing of metals in the last decade have enabled the creation of incredibly strong metallic microlattices that could never be created by traditional manufacturing methods. Because these materials are mostly empty space, they can be as strong as steel, but as light as plastic. We want to use these lattices to assemble complex structures from millimeter scale repeating cells to operate in certain extreme environments of interest to the lab. Here, Powerful pressure waves can arise in materials, reaching pressures as high as several 100,000 times atmospheric pressure in billions of a second. These waves interact with their environment in a complicated way. Think of the spreading, interfering pattern of ripples when you throw a handful of gravel into a pond. These complex dynamic interactions can cause materials to fail in unusual ways, and we don't know how lattices will behave under these loads. Before we can use these materials, we need to understand how they perform and what advantages they offer, and we can leverage Lawrence Livermore's expertise to do this. The lab is an advanced manufacturing laboratory that can print these lattices. The lasers at the National Ignition Facility, or NIF, can replicate these extreme loading environments. But this testing is incredibly expensive. So how do we pick what samples to test? To answer that, we think about design. In the same way we want our buildings to stay standing after an earthquake, we want lattices that aren't destroyed by these incredible pressures they're faced with. I began with computational optimization using our in-house code AL3D to tune the properties of lattices and simulate testing to look for designs that survive. I discovered that this cannot be done unless you add a thin skin of solid material on top of the lattice, which changes the incoming pressure wave enough to allow it to survive. This is an incredibly important finding because by tuning the thickness of this sheet, we have a new design variable we can manipulate for different environments. Of course, this isn't groundbreaking unless I can actually test these designs and prove that they work. And that's where the manufacturing lab and NIF come in. I had titanium microlattices printed on site, and I used the lasers at NIF to hit them as hard as I could. And they worked. One of my lattice designs withstood a pressure over 100 times greater than you would experience at the bottom of the ocean's deepest trench. My work has shown how to design a new class of materials to survive extreme loading conditions. It also drives home that doing science in the national interest requires fundamental research in material science. The materials I develop here will make their way into the next generation of mission-critical machines and components and allow them to operate under conditions once thought to be unsurvivable. Thank you.
Thank you, Brandon. Trivia question number 9. Are you ready? She's like, fingers should be hovering over buttons or something. In an episode of the CBS show The Big Bang Theory, Sheldon Cooper unsuccessfully pitched a collaboration request to this Berkeley Lab astrophysicist and Nobel laureate at a conference. Which Nobel laureate did Sheldon meet? Was it Saul Perlmutter, Francis Arnold, Stephen Chu, or George Smoot? Are you at Lawrence Berkeley National Lab? I would like someone who's not at Lawrence Berkeley National. Sorry that I've started to become hardcore, but anyone that's not at Lawrence Berkeley National Lab want to take a stab at this? It's multiple choice. You're not risking that much. Come on, let me see a hand. You're sitting awfully close to Lawrence Berkeley, people. Oh, yeah. You're pointing and said somebody. All right. Can I trust you? You're okay. You can trust me. I'm from Sandia. I like that. Do you know, or are you going to guess? What are you going to guess? B, Francis Arnold. Incorrect. Sorry. She won it too recently, I think. So we have 3 more choices. It's an astrophysicist, if that helps. Hold on. You answered. You already won one? How many gifts can you take home? Hold on. Come on. There are only 3 choices. Somebody. Yes, over there. Who? Enter A, Saul Perlmutter. Incorrect. It was George Smoot. That is correct. George Smoot. A very funny astrophysicist, by the way. And that's the correct answer. What kind of prize? There were only 2 choices left. Should get like half a prize. Oh, so you had a little bit of knowledge because you knew Stephen Chu wasn't an astrophysicist. Which of those 4 was Secretary of Energy under President Obama? Anyone? Thank you, Stephen Chu. All right, our 10th finalist. We're getting very close. Coming to us from coming to us from Sandia Lab. The name of her talk is Preventing the Next Pandemic, Identifying Host Proteins Conserved for Viral Entry. Please welcome Iris Jones.
The end of the world as we knew it. For many reasons, that's what the COVID-19 pandemic felt like. From lockdowns to social distancing to just devastating mortality rates, COVID-19 changed life for many of us. Unfortunately, the virus that causes COVID-19, SARS-CoV-2, is continuing to mutate, evolving to evade immunity that has been created by previous vaccinations and infections. Now, new vaccines are constantly being developed, but this is a very time-consuming process and requires vaccinating the entire population for every new variant. Just this summer, several new variants emerged with immune-evasive properties, reminding us that we urgently need new therapeutics that can be deployed rapidly, that will remain effective against new variants, or that can be used for people who simply cannot be vaccinated. In order to do this, our group is looking at human proteins that the virus commandeers in order to infect and replicate within cells. This works because viruses are so small that they simply cannot encode everything they need to reproduce. As a case in point, I recently identified a protein called MPC1 that is required for SARS-CoV-2 to infect cells. This works if we block the protein in the lab in cell culture models. We don't get infection. Now, not only do we not get infection with the SARS-CoV-2 original virus, but we also don't get infection with several Omicron subvariants, including one that is very closely related to one of the newly emergent immune-evasive variants that is now circulating. The cherry on top of this is that we identified this protein because it was identified by others in previous research as being essential for a completely different set of viruses. Ebola, Marburg, and Sudan viruses. Viruses that, like I said, are unrelated to SARS-CoV-2, but that have extremely high mortality rates. This makes the protein that we identified a very promising, broadly effective antiviral target. Finding targets like this one is the goal of our research, and future work will expand this concept into other viruses so that we are better prepared for the next pandemic, whether it is caused by another coronavirus, a filovirus, such as Ebola, or an as yet unknown virus, disease X, so that one day, although the world as we know it may end, it will be for the better, so that we can reduce and hopefully one day eliminate illness and death that has been caused by viruses that have plagued humanity for all of history.
Thank you, Iris. Have I intimidated you from raising your hands yet? Our next trivia question. What are the 3 DOE Office of Science user facilities here at SLAC? Not multiple choice. I suspect this is going to have to be a SLAC version. Can someone who's not at SLAC, does anyone have an idea? Does anyone at SLAC know? Am I going to get the prize for this one? Yeah. 2 out of 3 ain't bad. That's pretty good. He should get a little consolation. Cryo-EM, no, that's not one of our user facilities at SLAC, I guess. Also 2 out of 3, and you hallucinated one like you're an AI. Yes. It is LCLS, SSRL, and FACET. 3 impenetrable acronyms. Okay, so we are down to our final 2 finalists, if that's not a little redundant. Our 11th finalist comes from right here at SLAC. The name of her talk is Cutting Plastics with Stylish Catalysts. Please welcome Özge Bozkurt.
Particle decides to use a silence to identify the whole interest. The silence has the moment and the truth to cut the grass to make new into a crop top and a fashionable new skirt. At Slack, I'm in a research project using a similar approach to give new life to plastic waste. Think about your food, beverage, detergent containers thrown away after single use. These plastics are polymer units with repeating monomers. The selective cutting is done by the catalyst. Basically, metal nanoparticles immobilized on a solid support. Cobalt nanoparticles cut the polymer chain into its monomers to make new plastics, while ruthenium nanoparticles prefer to cut into shorter chains to be used as transportation fuels. The styling world is at macro scale, while catalysis world is at nanoscale. We cannot see these tiny nanoparticles with naked eye. Think that your fingernails grow 1 nanometer per second. My collaborator uses an electron microscopy technique to form images of these nanoparticles. Ruthenium nanoparticles are about 2 nanometer in diameter. There are hundreds of atoms in 1 nanoparticle, and at Slack, we want to look closer. Here, we have powerful and tunable X-rays to study materials at atomic scale. If you want to study ruthenium, I send into my catalyst with an X-ray beam of specific energy for the ruthenium element. The X-ray beam passing through the atoms, colliding with the neighbors, loses intensity in the exit. I am collecting these exiting X-rays and determining the distance between 2 ruthenium atoms. By using this fancy X-ray based technique, I am helping my collaborator to design stylish catalysts to cut plastics into useful products. I encourage you to recycle your plastic waste so that they can visit our catalysts in the future for new lives. Thank you.
Thank you, Ozge. Trivia question number 11. What dinosaur pictured here, perhaps, not really sure about that. What dinosaur did Sandia scientists help to recreate the vocalization of? Not written by an English major, ending in a preposition. But this is a science research slam. What dinosaur? Yes, sir. I don't know what you said, but it can't possibly be what I see in front of me. Another, come on, who knows their dinosaurs and their vocalizations? Someone want to name one dinosaur? What? That bird? Oh, bird. No, but yeah, birds are dinosaurs. And in fact, I'm going to talk about that in a little while. But wrong. Diplodocus? Incorrect. I think this is a tough one to not be multiple choice because there's only, how many species of dinosaur? Anyone else want to try or should? Yes. Not right. I know the picture maybe made you think brontosaurus, but not. It's a tough one. How do we handle this situation? Do we make every person in the room take a guess before we keep the prize to ourselves on this one? I'll take a guess. The reason I don't even want to take a guess is it's challenging to pronounce. It's actually, can we have it up on the screen? It's Parasaurolophus. Parasaurolophus. Using powerful computers, computed what? Is it really? Okay. So how were you involved in the research exactly? Really? You remember this? What lab are you from? You're from Slack. This May, on trivia question 11, we may have the first example of someone from a different lab knowing about the research at a lab they're not associated with, using powerful computers, computed tomography, CT scans, and a rare parasaurolophus. How do you pronounce that? It looks like it needs another syllable. Yeah. Parasaurolophus skull. Scientists at Sandia and the New Mexico Museum of Natural History and Science recreated a low-frequency rumbling vocalization of a crested dinosaur that lived 75 million years ago. Okay, so sorry about that. You were correct. And give the man a prize. So I'm about to introduce our 12th and final finalist. And then we're gonna go through, the show's not over yet. And we're gonna dismiss the judges and let them go do their, let the judging commence. So let's meet our 12th finalist, coming from Lawrence Berkeley National Lab. The name of her talk is Sorghum and Me, A Complicated Relationship. Please welcome Anvia Kasten.
What if you had a partner who was perfect for you in every way, except for one thing? They're too stubborn to accept any attempts to change for the better. Would you give up on them or try to make it work? That's my dilemma with sorghum. Sorghum, or the king of millet, is the 5th most important cereal crop in the world. It's grown in over 30 countries and feeds 500 million people. But it's not just a food crop. It's also a powerhouse of bioenergy that can be grown in harsh conditions and produce more biomass than any other crop. Tapping into this abundant biomass and converting that into renewable biofuels, sorghum could be the green crop of the future. That solves our energy crisis. The catch: it's not easy to convert sorghum biomass into biofuels. Our solution? Genetic transformation, a process where we introduce new genes into the plant to improve its traits. For example, we can introduce genes that would increase the digestibility of sorghum biomass. Genetically modified sorghum. Sounds easy, right? Nothing is ever easy. You see, sorghum is notorious for being one of the most difficult crops to genetically transform. Growing sorghum in culture plates in the laboratory is immensely labor-intensive and requires the perfect combination of ideal plant tissue, light, nutrient, hormone. Oh, I could go on and on. But basically, what I am saying is that sorghum is the bad boy of crop genetic transformation. It's hard to tame, unpredictable, and always a challenge. My goal is to improve sorghum transformation so we can maximize its potential as a bioenergy crop. To do this, I decided to borrow some wisdom from its more successful relative, wheat. Wheat has genes to make it easier to regenerate in the laboratory, so I thought maybe they could finally tame this bad boy. I introduced these genes using a soil bacterium through a natural infection process, and sorghum must be really liking these genes because I have seen an increase in the transformation efficiency. This new method opens possibilities for sorghum improvement. Imagine a genetically modified super sorghum, so efficient at providing us biofuels, it reduces our dependence on fossil fuels and mitigates climate change. I see sorghum as the bioenergy crop that could save our overheating planet. But with the challenges I face with genetic transformation, I could also see how this crop is so easy to love and just as easy to hate. So if you ask me about my current relationship with sorghum, yes, it's complicated. Don't worry, we are making it work.
Thank you. Thank you, Anne. And we do have also one final trivia question. In 2008, Berkeley Lab scientists mimicked the structure of this sea creature's exoskeleton to create the toughest ceramic ever produced. Which type of sea creature was it? A crustacean, a mollusk, an echinoderm, or an unpronounceable cnidaria? I think can I get a vowel between the C and the N? Who named these creatures? But it's multiple choice, very low risk. Yes, sir. Mollusk. That is correct. Oh, and I like that. I could tell by your expression you were guessing. You were surprised. You were more surprised than anyone else. So, all right. That is our final question. Those are our 12 contestants. Could we have a nice round of applause for our 12 contestants over there? Like I said, this has been probably a months-long process. Each individual lab solicited speakers and finally selected their finalists to send here. So it's been a long time coming and they all did a fantastic job. Here's what's going to happen next. First of all, I want to explain the People's Choice voting instructions. So if you're watching on YouTube, in the chat, there will be a link and you can use that link to participate in the People's Choice. If you're here, we have a QR code that will launch that link if you can get it. And we have, how much time we have? Wasn't there something on here about how much time they have? About 10 minutes you have about 10 minutes to participate in that vote. So there will be a People's Choice Award. And for the regular competition decided by the judges, we are now going to send the judges to do their job, tally up the results, and help us decide who came in second place and first place. And then, of course, there will be the big tally that tells us which lab did the best. So, judges, you can go to your secret judging chambers. And while they're gone, I'm going to talk to you for a few minutes. Right? We'll give them a moment. All right. So, oh yeah, I'm going to give you a minute because before I try to be funny, it would be nice to have some of your attention. So if you're take a minute and do the People's Choice. Is it working? Are you getting the link? I'm going to give you a minute to do that. I don't want to see you contestants pulling up that QR code. It's the People's Choice. You're not people. You're scientists. We all know you're not really people. Half of you are probably AI already. Yeah. But best jacket. I'm sorry, no offense to anyone else wearing a jacket, but he went all out on that. So, yeah, I don't know how much the form requires. You just have to, is it multiple choice and you choose your, excellent. So, I think we have probably about 10 or 15 minutes and I'm just going to reintroduce myself and say, I'm Brian Mallow and I'm a science comedian. I'm not a scientist, as I mentioned. I'm just a comedian, and I haven't always been a comedian. It's the best job I've ever had, but I haven't always been a comedian. In fact, I used to be an astronomer, but I got stuck on the day shift, which sucks. You don't discover anything good. No offense to solar astronomers or radio astronomers or any astronomers, because they all work on the day shift now. So yeah, I've always been a night person. Even when I was a kid, I used to hate it when my parents made me go to bed early. I would fight about it and lose, but on my way to my room, I'd say something like, well, you can make me go to my room, but you can't make me go to sleep, which probably would have been true, except my dad was an anesthesiologist. No, Dad, not the mask. Oh, My mom would come up a couple hours later, tuck me in, check the IV and the EKG. I'm also, you know, I'm very conscious of my posture. And I think it's because when I was a kid, my mom used to always tell me to stand up straight. Did you ever get that one growing up? Stand up straight. It's such a mom thing to say. I think mothers have been telling their kids to stand up straight for longer than we realize, perhaps even to pre-human days. What if that were the driving force behind the evolutionary trend to walk erect? Mothers nagging their children up the evolutionary ladder. Stand up straight. Don't drag your knuckles when you walk. What are you, born in a tree? I noticed a long time ago, I've always had, so I'm not a scientist, but I was really heavily influenced by science fiction. And when I try to back engineer my path, like science fiction and science, especially people like Arthur C. Clarke and especially Isaac Asimov. Does anyone know who Asimov was? You probably think of him as a science fiction writer, but you know what? He was a PhD in biochemistry turned writer, and he published about 500 books in his lifetime. And it's way more nonfiction than fiction. He wrote in every discipline of science. He wrote history. He wrote mysteries and limericks and memoirs. It's often said of him that he wrote something in every category of the Dewey Decimal System. And I don't know if that's true, but I love saying it. So it's plausible. He wrote an annotated guide to the Bible. He wrote an annotated guide to Milton's Paradise Lost. He wrote a lot. And I feel like, yeah, and he also was the best science explainer. He could take you to a complex place without losing you. And there's a real art and science to that. And there's a famous quote by Asimov that you may have heard. I love it. It's the most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny. I love that. And I resonate like as a comedian. It's not just for scientists. It says something interesting about the scientific process, but that's how jokes start a lot of times too. Like for me, I spend a lot of time in airports and I don't smoke, but I think some smoking restrictions are a little extreme, maybe even comical. My favorite example is, there's those like at airports, you can't smoke anywhere except there might be these special glassed in rooms. I love those. It's like a terrarium in which you can view the smokers in a recreation of their natural habitat. If you haven't seen one of these, get to an airport. It's worth the price of admission. They'll have a lounging area, a pacing area, because the smokers need their exercise. You know, if you come at the right time, you might see a couple out basking on rocks, fighting amongst themselves, grooming each other. Parents are bringing their kids up to read the little plaque describing the species. Oh, Homo emphysemus, I see. An endangered species. The only thing they don't have is one of those coin-operated machines so you can buy cigarettes to toss out to the smokers. That would complete your little zoo experience there. I noticed a long time ago, whenever my mom would lose weight, my dad would gain weight. And when my dad lost weight, my mom gained weight. It was like the conservation of mass within our family. I had a theory that you never actually lose weight. You just give it to somebody else. Fat can be neither created nor destroyed. It's one of the basic laws of the universe. I had a frightening experience. So I used to live in San Francisco. It's really great to be back. I haven't been here since well before the pandemic. And it's great to be back in the Bay Area, but I'm over at Berkeley and I had a very frightening experience the other day. I'm sitting in a cafe and I noticed in the display case behind me, someone had put pasta and antipasta right next to each other. Are they out of their Vulcan minds? That was Vulcan with a V. I don't need to get fired. Yeah. So, I thought I would say something a little, since this event is about science communication, I thought I would tell you a little story and use some examples. It's some of my favorite science communication advice. And it comes from Richard Feynman, the Nobel Prize winning American physicist. And in fact, like it was mentioned earlier that this week, the Nobel Prizes have been announced. And I'm sure most people here kind of know this, but you know the origin of the Nobel Prize? It was funded by Alfred Nobel with the fortune that he made from his invention of dynamite. And the significance of dynamite is that it was the first relatively stable and usable form of nitroglycerin. And other people were working on solutions, but he was the first to survive the R&D phase. So it's the Nobel Prizes. Richard Feynman Great storyteller. And if you want, if you Google this, you can hear, I found this online. You can listen to audio of him telling you this story. Feynman said that his father used to read to him from the encyclopedia. He'd read to him from the encyclopedia. He'd sit him on his knee. I think he was a child at the time. And he would find like an entry about dinosaurs, for instance. And he'd say, he'd read this bit. He'd say, go, this dinosaur could attain a length of so many feet. And he would stop and he'd put the book down and he'd say, you know what that means? That means if this dinosaur was in our front yard and you looked out your second-story bedroom window, you could look him right in the eyes. So he translated the bare facts into what it really means. And I love that. I resonate with it. It hit me like an analogy I haven't come up with yet. And I think about it in my own writing and stuff. And here's a couple examples. Here's what it means to me. This is a couple examples. The International Space Station orbits the Earth at about 17,500 miles an hour, which is obviously, it sounds fast, but that's a number that's so outside our daily experience, it's kind of hard to connect with. But what if I told you that's almost 5 miles per second? And that means if you were in space and the ISS went by, in 1 second, it would be 5 miles away. 17,500 miles an hour doesn't even come close to capturing that. And it's the size of a football field, I might have said. Here's another example, Pangea. A couple 100 million years ago, instead of this sad state of affair with all these separate continents, there was just one giant landmass, Pangea. Well, you know what that means? International travel was really easy. You want to go to Germany? It's right over here. Amsterdam, just step this way. Australia even, Bernard. And my favorite example, so I've done a lot of science communication stuff. I went from comedian to science comedian. You know what? So I was always a science geek. I loved science first. So when I started comedy, it was quite natural for me to be very geeky with my comedy, but it took a long time before I came up with the phrase science comedian. And I was like, huh. And sciencecomedian.com was available, which I thought was either a really good sign or a really bad sign. Maybe it's useless real estate, but really that sort of crystallized my thinking around it. And it's like, oh, if I cut this other stuff away, science comedian, that's what I do. That led to science communication stuff. So I made science videos for Time Magazine. I did stuff for Neil deGrasse Tyson's Star Talk Radio. I did little monologues. And I blogged for Scientific American. And I spent 4 years working at a science. In fact, that's why I left San Francisco. I never would have imagined moving to North Carolina, but I was living in San Francisco and I took a job at a great museum in Raleigh, North Carolina, the North Carolina Museum of Natural Sciences. And I worked in communications for 4 years at a science museum. So I've done all these different science communication things. And while I was at the museum, I learned from our paleontologists that birds are dinosaurs. Now, does everyone here know that? Because when I was growing up, I think we heard that birds are related to dinosaurs or descended from dinosaurs. But the fact is today, birds are taxonomically categorized as avian theropod dinosaurs, right? So, you know, there's like, I only know about these two basic dinosaur shapes, like, you know, the brontosaurus shape that we saw earlier, pointing to the place where it no longer exists. But a brontosaurus, those are sauropods. And then there's, you know, the theropods like T-Rex and Velociraptor. I can only name dinosaurs that were in Jurassic Park. I'm kind of a bad science comedian. But, you know, the ones with birds, so T-Rex and Velociraptor, those are non-avian theropod dinosaurs. But birds existed before the extinction event 65 million years ago. And when, along with so much of life, every other group of dinosaurs was wiped out, some of these birds survive. And so today, it's not even close to being accurate to say dinosaurs are extinct. We think of dinosaurs being extinct. Just like Pluto is no longer a planet, this is not the case. Dinosaurs aren't extinct. There are 10,000 living species of dinosaur. They're on every continent, and their diversity is beautiful. There's a hummingbird that weighs less than a penny. That's even hard to conceive. There's an ostrich 9 feet tall, weighs 300 pounds. There's penguins and peacocks and murmurations of starlings carrion eaters and birds of prey. The bald eagle, symbol of our nation, is a dinosaur. So is Donald Duck and Tweety Bird and the Roadrunner. Corvids, like crows, corvids are clever tool-using dinosaurs. Parrots are talking dinosaurs. Blackbird singing in the dead of night, that's a song about a dinosaur. And so is Freebird. And I know why the caged dinosaur sings. Here's how not extinct dinosaurs are. Most mornings when I wake up, the first thing I hear is the cries of dinosaurs outside my dwelling. I get up and I have dinosaur eggs for breakfast. I go out to my car and a dinosaur has desecrated my car. From the looks of it, many dinosaurs, a whole gaggle of, a parliament of, a murder of dinosaurs has pooped on my car. That's what I mean by desecrate. If I had to make that clear, I was using jargon. You know what? Dinosaurs pooping on buildings is such a modern problem. There's an entire industry that makes those countermeasures. You know those spiky things on buildings? Do you know what they're called? Bird control spikes, or pigeon spikes if you feel the need to single out one group. On Thanksgiving, almost every non-vegetarian in America has the same dinosaur for dinner. Colonel Sanders built an empire on his recipe for fried dinosaur parts sold by the bucket. So we know what dinosaur tastes like. It tastes like chicken and turkey and duck and pheasant. And if somebody has a small appetite, what do we say? She eats like a bird. How did that dinosaur become the standard for eating light? Photosynthesis, that's eating light. Thank you for the slow burn on that one. I know you don't have to tell me that was a long way to go for that pun. Do you like puns? Is that it? Was that a no or a yes? Because maybe if you say no, I'm going to punish you with a bunch of them. If that's the way you want. Either way, you say yes, here they come. You say no, here they come. Maybe I'll save it. So hold on. We'll have some more puns. I've been really conscious of aging lately. I mean, I already had a birthday this year, which I know sets me apart from no one, but we all age at about the same rate unless you drive really fast. Thank you. Thank you. It doesn't matter. It's a relativity joke for some people. For other people, it's just nonsense. Anyway, yeah. I just want for myself, I just want to age gracefully. That's what I hope for myself. Like I have gray hair. I've had gray hair for years. I don't care. I'm fine with it. I don't care if it goes all gray and then blue and then ultraviolet, just naturally. In fact, that's what I'll say if I lose my hair. I'm not bald. I have hair. It's just outside your visible spectrum. Okay, you know what I'm talking about. Actually, you want to hear this? I care about my jokes actually being scientifically accurate, which is weird, right? Like for a comedian, you know, a comedian doesn't have to, but I care. So most of my jokes I think are accurate, but that joke I just told, so I don't know if you remember, but originally YouTube had some messaging. You could message people on YouTube. They removed that. Many years ago, that gray hair joke, I had it on YouTube. And one day I got a message from a 13-year-old boy in Serbia. And he wanted to point out to me the flaw in that joke. And does anyone know what it is? I've already pointed out the joke. It's this. Does anyone see something really wrong with that? I said that, like, I want my hair to go gray, blue, ultraviolet, and then it's outside your visible spectrum, right? But the thing is, if my hair just reflected ultraviolet light, and that's what you saw, and if you couldn't see that, it wouldn't make it transparent. It would just appear black to us. So you wouldn't see his bald head. He doesn't have, if he had ultraviolet hair, it would just look black to us unless you could see into the ultraviolet. So this 13-year-old boy schooled me on this physics one, and I was like, oh, wow, you're right. But I'm not dropping that joke. I like it too much. It's too funny. It always gets a laugh. But I might sometimes point out to an audience where the mistake was. So here's another one. I saw a movie recently with my friend Chuck. And I don't like seeing movies with Chuck because he always has to sit in the front row because he thinks he gets to see the movie before anybody else. And you can't argue with him because he always has the same last word. The speed of light is finite, Brian. And it's true, but the speed of light's very fast. Does anyone know the speed of light? Shout it out. Technically correct. C is the speed of light, but come on. I'm sorry, I forgot to mention I'm an American and I don't know what that gibberish was you were just saying. The metric, we can't handle round numbers of 10. The number I'm looking for, I divide by 1.6. Yeah, that, you know what's so funny? You are the second person to say that to me. And the other one was, there's this event that I participate in for like 7 or 8 years. It's called the Lindau Nobel Laureate Meeting. It's in Lindau, Germany. They bring a bunch of Nobel laureates together and hundreds of young scientists from like 100 countries to be mentored for a week. And I performed at the opening ceremony. And in addition to all these, it was a physics meeting, they're themed. So there were all these physicists, but there's this other meeting that spun off, and it's the Heidelberg meeting. And instead of Nobel laureates, it's all about math and computer science. So there's no Nobel Prizes for that. But what their meeting is about is people that won what are like the Fields Medal and other, the almost the equivalent of Nobel Prizes in computer science and math. And so what they've evolved is this relationship where every year at Heidelberg, one of the Lindau laureates will be there. And every year at the Lindau meeting, there will be like a computer scientist. So the year I was there, I was performing, the president of Austria was in the room, and there were these laureates, and I only recognized a couple. I recognized Stephen Chu. I recognized George Smoot from the Big Bang Theory. And I recognized the computer scientist, Vint Cerf. Do you know who that is? He's sometimes called father of the internet. He and a partner developed the protocols that the internet is based on. And I know him for the weirdest reason. I use Final Cut Pro as a video editing tool. And I got this video course, and in the samples, Vint Cerf was it was interviews with him. So I've just been aware of who he is for a long time. So I'm performing. I tell that joke. I say, I can't handle the metric system. And Vint Cerf goes, just multiply by 1.6. This was 7 years ago. And you're the only other person who has said that. And he goes, it's easy. And I said, yeah, for the father of the internet, maybe. And I wouldn't have been able to say that for almost anyone else in the room, but it was him. So anyway, personal story. That was just too weird. So any questions? We got a few more minutes, I think. Did I tell you I went to a magnet school for bipolar students? Did I ever tell you that? It's a true story. I was talking about aging. We change our behavior as we get older. Like I noticed my ex has started dressing in bright colors, I think to trick predators into thinking she's poisonous, maybe. No, and I'm not being mean or anything. She was great. We're on great terms. She's good. You know what? She was a lot shorter than me. I'm not very tall. You know, don't be fooled. You're sitting down, I'm standing up, but I'm not even this tall. But she was a lot shorter than me. In fact, the first time I saw her, I thought she was farther away than she actually was. And I can't even make fun of that because you know what? I've never been very tall. I peaked, past tense. I peaked. That's where this joke is going. It's not a joke. I peaked at 5'7.5". And when you're 5'7", you count the half. I never lied and said 5'8", but I always included the half. And then one year I go to an annual checkup at the doctor. They measure my height and he goes, you're 5'7". And I said, and a half, right? And he's like, no. And I'm like, no, what? And then a couple of years later, some years later, I wish I had the data to show you on a graph. I don't know. But some years later, they have the records though. That would be interesting. I get measured. He goes 5'6.5". No way. And I believed him because I believe all my abusers. And it's like 5'6", and I checked your measuring stick. This cannot be correct. And then just a few months ago, they tell me so what do we go? 5'7.5", 5'7", 6.5. So I'm down to 5'6", a new low. Great for a golf score or something, but not what I want to hear. And you know, so you know what's going on here. You know what this is. This is gravity over time. This is a measure of how long I've been on the planet. You want to know how old I am? 1.5 inches of crushed spine. That's how old I am. And this is a very disturbing trend because also, you know what? So my height's going down, but my weight is staying pretty consistent. So I'm just getting smaller and denser. And this is a very disturbing trend. You know where that leads? I'm going to be a black hole. That's the ultimate smaller, denser black hole. Everyone beware. You won't be able to see me like your hair. Okay. I hope you can handle me picking on you. All right. So have you ever looked back at your life and tried to figure out where the screw-ups began? Like, where was the first one? I was a cesarean birth. So right there, birth, I screwed that up right out the chute. I didn't even come down the chute. I busted out some side exit. I think that's why I have a bad sense of direction, because I was a cesarean birth. I'm half serious about this because look, there I was, 9 months in the womb. When it came time to leave, I started heading for the exit, which was clearly marked. Suddenly there's a shaft of light from behind me. Two of the biggest hands I've ever seen are pulling me this way. I'm going, it's this way, right? Like, no, this way. I'm going, I'm sure this is where I came in. Did I lose you in the middle of that? Did I misspeak? You fell behind somewhere there. Okay, so I'm going to tell you a series of jokes and I'm going to start with a little story. So several years ago, I did a show at a science museum in Washington, D.C. And when it was over, it was a really good show. Use your imagination. It was a really good show. And they asked me if I could come back the next year with a whole new act. Comedians love hearing that. Could you come back next year with a whole new act themed to go along with our new exhibit on infectious disease? Now, this is 10 years ago. This is way pre-pandemic. So they wanted a comedy show with an infectious disease theme. And I said yes, because I wanted the gig. But then I was like, what have I committed to? But that led to me doing a lot of thinking about infectious disease and viruses. So I said, I started thinking about viruses. And again, like now we've been thinking about viruses a lot, but what I was thinking was like just how fascinating, you know, they're so tiny, their genome is so small. They're not really quite what fit our definition of life because they can't reproduce on their own. But when they get inside a cell, the way they take over the cellular machinery is amazing. It's like a hostile takeover, like your cells under new management. And if you think about this stuff too hard, here's the kind of jokes you come up with. A virus walks into a bar. The bartender says, we don't serve viruses in this bar. The virus replaces the bartender and says, now we do. An infectious disease walks into a bar. The bartender says, we don't serve infectious diseases in this bar. The infectious disease says, well, you're not a very good host. Two bacteria walk into a bar. The bartender says, we don't serve bacteria in this bar. The bacteria say, but we work here. We're staff. A room temperature superconductor walks into a bar. The bartender says, we don't serve any superconductors in this bar. The room temperature superconductor leaves without putting up any resistance. An infrared photon walks into a bar and says, is it hot in here or is it just me? A neutrino walks into a bar. The bartender says, we don't serve neutrinos in this bar. The neutrino says, hey, I was just passing through. It's good to have physicists in the room. Thank you. Schrodinger's cat walks into a bar and doesn't. A statistician walks into just your average bar. The bartender says, we don't serve statisticians in this bar. The statistician says, well, you're just mean. A radio wave walks into a bar. The bartender says, can I get you anything? The radio wave says, no, I'm just here for the reception. 10,000 electrons walk into a bar. The bartender was shocked. The Higgs boson walks into a church in Geneva. The bartender said, they aren't really, they have wine, but there aren't really bartenders. Okay, the priest says, we don't allow Higgs bosons here. The Higgs boson says, but without me, how can you have mass? I think finally, thankfully, some helium gas drifts into a bar. The bartender says, we don't serve noble gases in this bar. The helium doesn't react. Thank you. We'll end on that one. I'll tell some more because our judges aren't back yet. How are they doing? Oh, 5 more minutes. Is that what they told you? It's a tough decision. Are you feeling tense? Are you sweating? How do you feel about it? How do you think it went? How do our contestant think it went? Did it go like a week? I don't know why. Is that oh yeah? Because you slipped the judges some money or something? Or you're like, kind of grim. It's not what I expected. Or well, what does this one mean? Googly eyes. How did you feel good about it? It was the second time you all there was a tech run through today and everyone gave it. Did anyone feel like they did better at the tech run through than they did at the actual show? No. I think you all did great. Congratulations. Fantastic job. Well, thank you again. I like IMAX movies too. And I think my favorite IMAX film that I ever saw, it was called Everest. It was a documentary. It wasn't that narrative film about Everest, but it was a documentary about a team of climbers that made it to the top of Mount Everest with a film crew. That doesn't make it any easier. I remember I told my mom about the movie and here was her only comment. She goes, oh, I could never do that. It's so cold up there. Like that's the one reason she hasn't climbed Mount Everest. Like she was about to ever at any point in her life, never mind the 5-mile ascent up rock and ice, slippers on her feet, cigarette dangling from her lips. But no, you didn't tell me it was chilly at the top. No way. Deal's off. I didn't know it was going to be cold on Mount Everest. Right? 5 minutes. I want to time this well. I'll tell a couple more. You know, one of the things we were going to do is we were maybe going to talk a little bit about, let me ask you this one. I think geeks have the funniest arguments, and I self-identify as a geek, by the way. Does anyone else here? By applause so we can hear you. Yeah. I don't know if you prefer a different term, if you like nerd, whatever. I like geek. I like geek more than nerd or dweeb. That's just mean. And I like, there's other one. No, but geek, nerd, geek especially. Nerdy is good. I think geeks have the funniest arguments, and because we can argue about the stupidest things. And in fact, the less important it is, the more vehement the argument sometimes, right? So one time I was at a party with museum people, and one of the astronomers from our museum, he's really geeky. Also, he's an astronomer, but he loves comic books and all the movies based on comic books. So one day he asked me, what if I could have any superpower, what would I have? Let me put that to you before I tell you our answers. What's a superpower you would like? Just yell it out. I mean, but maybe what? Teleportation. That's what Bernard said. I was talking to him earlier. Teleportation would pretty be amazing. And you know what? I have been working on teleportation for so long and I just haven't gotten anywhere. Thank you for that setup. I did not pay her. Oh, they're here. All right. Well, let's welcome our judges. Right? Okay. Let's welcome our judges over here. No, this time you're on this side of the table. Again, our national lab directors from the Bay Area. Can I ask you, was it hard? Yes, of course it was. Yeah, very challenging. Did you go to like, how many decimal places did the judging go to? Yes. So, but this is the nature of this contest. It takes 4 directors of national labs to come to a conclusion. Okay, so the order of things, first the People's Choice. All right, so we solicited votes from our audience here, from our audience on YouTube, and our People's Choice Award goes to Anvia Caston. And gets this beautiful certificate. You know, congratulations, good job. This is for you. It's all you get. There's no cash prize. I didn't tell you. So for those of us watching, that this contest is about bragging rights, and it's about this certificate. And do we have 2 certificates for second place and first place? Okay, so 2 more certificates coming up. And is that the next thing? What? Okay, we're gonna do, oh yeah, so we're gonna have a little photo. You get a photo opportunity with the lab directors as well. All right. For lighting purposes, this is the angle. You don't always get this view of our lab directors, so take it in. Behind the scenes, so to speak. Congratulations, Anne. Oh yeah, where was Anne from? Anne was from Lawrence Berkeley Lab, by the way. And okay, that was our people's choice. Now this is the contest and the decisions made by our panel of esteemed judges. The certificate for second place goes to one of our contestants from, this is second place, one of our contestants from Lawrence Livermore Lab, Wedi Mostopo. Wedi, congratulations. We're going to have our little photo shoot. Congratulations, Wedi. So our winner, our individual winner for the 3rd annual Bay Area Research Slam comes to us from one of the 4 labs in the Bay Area. And it's Lawrence Berkeley Lab. Ladies and gentlemen, it's Anvia Caston. And yeah. Congratulations. So our people's choice and our judges came to the same conclusion. Let's do another photo shoot. Now, interesting how the labs get this and the individuals get a piece of paper. But isn't that the way it is? So this trophy is for the lab who's cumulatively the points unrelated to the people's choice, but from our judging, which lab took the prize. In the first year, it was Lawrence Berkeley National Lab in 2021. In 2022, it was Lawrence Livermore National Lab. And tonight, maybe not surprising, it goes to Lawrence Berkeley National Lab. Do I give you the prize? Yeah, one of the judges. Does this seem? So congratulations. I think, Meg, I think you said earlier that you wanted to bring it back to Berkeley. And so the thing is, okay, that's both the people's choice and our judges chose Anne, but I'm sure it was an extremely hard decision because I wouldn't have been able to make the decision. One more round of applause for all 12 of our contestants. Fantastic job. In fact, let me just, they're not all in one place, but let me just give them props. So it was Anvia Caston, Ozge Postcode, and I'm going to probably miss some. This is so disorganized. And we had Addie Pradradi, and yes, Valentina Garcia, Sandy Ewan Gao, Wedi Mostopo, Karuna Wedi, Taran Driver, Bernard Field, Brandon Zimmerman, and Iris Jones. Did I got everybody right? Yeah. Fantastic job. The future of science. Thank you all for attending. Thank you for watching online. This will be on the Slack. This will be, if you want to watch this later, it's on the Slack YouTube channel. And that's it. How about another round of applause for our judges? Do I have them here? Yes. From Lawrence Berkeley National Lab, Mike Withrow. From Slack, John Sorrow. Thank you. And from Lawrence Livermore, Kim Badil. Sandia, Andy McElroy. Thank you, everybody. And we'll see you next year. And good luck with your research. Good night.
We need to do photos of all these people, like all the lab directors and the winner and all the 12 contestants.
Yeah. Hey, contestants. We want some more photo shoot stuff with you. So we're going to need at least a couple photos with all 12 of you.
We also need the 4.
Oh, and there's a reception in the lobby with refreshments for you.
Do this first. Photo of the 4 lab directors.
Mm-hmm.
And we'll just stand right here.
Okay.
And then you want to look at that? Sure. You can.
If our 12 contestants could come on over here.